So the original speaker on this session was a student of John Clark, who also worked in my group and was a postdoc with Michelle, who's very dear to us, Michael Hattridge. But he had a personal issue, so he was unable to join us this afternoon. So John, he does send you his regards. I just texted him. And we, of course, wish Michael well as well. So the topic that I chose for this particular presentation was something that has all of the above that we've heard about today. It has squids, it has some noise in it, it has some microwave readout as well built into it. And in particular, it was a topic that both John and Michael participate in various discussions with us. So I thought it would be appropriate to talk about this topic. The work here was done by graduate students Eli Levinson-Falk, Natanya Antler, and postdoc Vijay, and also postdoc Shehakan and Gorgi. The theory contributors on this work were Marvin Cohen and Leonid Glazman from Yale. And I think this picture basically says what we were trying to do. The idea was to look at squid structures that in fact were not realized by tunnel junctions, okay, that were realized by constriction type Josephson junctions, and to see, well, could there be useful devices that we could re-engineer using this particular building block? We've known for some time, of course, from the time of Brian Josephson and all the talks that we heard about today, that the tunneling junction, as exemplified by two superconductors separated by an insulator, is given by this characteristic relation where the current is really the sign of the phase difference across it, combined with the voltage relation that gives us something with this type of cosine potential. And indeed, if the height of this potential is chosen such that there are only a few quantized levels, we can talk about qubits. And in fact, if there are many such levels, we can talk about a classical anharmonic oscillator. So the idea that we had was, could we relax this constraint, this sine delta constraint, by using a very different type of geometric structure? And what would that mean? And in particular, at that time, we had two motivations. One was to think about Josephson devices that no longer had these amorphous barriers in between. Okay. Could we reduce noise due to decoherence from various fluctuators in this oxide? And number two, could we also think about applying such devices for molecular magnetism? Because one of the challenges with tunnel junction-based squid devices is that if you would like to effectively couple the magnetic field of a very small nanoscale or atomic scale dipole, that coupling is not very efficient with a large tunneling junction. However, it may be very efficient with a nanoscale feature like a weak link. So really, there were two choices to consider. One is this two-dimensional geometry for a Josephson junction, or historically called the Dayam bridge. The other option was to consider a three-dimensional or variable thickness bridge. And in particular, we started off this discussion and this work thinking that there may be very large geometrical differences between the current phase relation in these two structures, and we wanted to figure out how do you optimize, if you like, the nonlinearity in the current phase relation. Okay, this was something that was not obviously apparent in the literature for these two structures. So let me give you the known properties of these structures first before I show you about the analysis. The tunnel junction is a venerable structure because it always gives you a sign relation. And there's a very good reason for that. A 2D structure can give you a very linear type of current phase relation. And in fact, quite often it's hysteretic in the way that I've shown it here in DC characteristics. A 3D structure gives you something in between. It kind of looks like a sine wave, but it's not really a sine wave. You can see it's sort of pushed over a little bit and has a sharp part here. So how can we reconcile all these different features? The starting point was to look at existing works on the current phase relation, of which there are many. Right? There is the seminal work by Konstantin Likharev from '79 telling us all about different types of current phase relations, which was perhaps republished yet once more in this work by Golubov in 2004. The challenge was the structures we were looking at are aluminum structures, which has a coherence length in thin film form of order 30 nanometers. And we're considering widths and lengths that are between 10 and 100 nanometers at low temperatures. In reality, these particular sets of parameters are not well approximated by the closed form formulas in these papers. And in particular, at very low temperatures, they're really not approximated by these types of relations. So what does one do? One can calculate the pairing potential delta as a function of position on such a structure and as a function of temperature, and this requires our favorite Green's functions formalism to do this. all sorts of Gorkov formulas to calculate this. And in particular, we are not in the mesoscopic or ballistic regime. We could imagine that there is really diffusive transport still in the structure, in which case you can start off with these Gorkov equations and end up with the Usadel equations. Okay? And this is what these equations look like. Okay, I will spare you all the details of this theory, but it was a very productive collaboration with Jaideep Sao, who was a graduate student with Marvin Cohen at that time. Okay, and that was the subject of this PRL paper. So one goes ahead and tries to solve these Spinner-Green's functions. In particular, at finite temperature, we did an expansion in Matsubara frequencies. And with this in hand, you can calculate the current, okay, specifically through these junction structures. So here are the numerical results. So what I show you here are results for 2D and 3D structures shown for different lengths. So these are practical lengths that we can think about attaining in some sort of lithographic process. Okay, we have a length, if we're very optimistic, of 15 nanometers, say. 45 nanometers is a very reasonable structure to produce. 240 nanometers could be produced quite some time ago. Okay. So if we look at this for something that has 600 nanometer contacts for 30 nanometers of aluminum at 150 milli-K, all reasonable parameters for operating such a device, you can see here in the two-dimensional structure you reproduce this kind of sawtooth pattern that we see here. And in reality, if you look at the 3D structure for the short curves, it's again starting to look very much like this sine wave that we had before. So indeed, there's something very different, right, in looking at these structures. And in particular, if we made it wider, 45 nanometer width, you still recover the same kind of behavior. So this gave us some encouragement, saying that we could probably produce something that is weak link based, but it's pretty close to the Josephson tunnel junction that we love. Right. So I want to say a few words about why this difference occurs. It was, of course, Marvin Cohen that pointed out to us that this is totally obvious. And it was obvious also to Likarev. We just could not understand his paper when he wrote it in '79, where he had this comment, why would you ever use 2D weak links? That's all the comment said, so we didn't really understand what that meant. But Marvin at least explained it to us and said that really what was happening is we are solving these Usadel equations. They are in reality a solution of Poisson's equations. And a solution of Poisson's equations in 2 dimensions always has a logarithmic solution. Right, so in fact, what you're trying to do is to make a Josephson junction, a good Josephson junction, where the phase drop should be across the Josephson element. That is guaranteed in a tunneling junction because you don't have pair states inside. Right? In a wire structure in 2D, you can see the phase very smoothly goes across the junction. So these are contours showing you here that we would like to have the junction here, but in reality, the phase is being modulated in the contacts, and it doesn't do that in 3D. Right? The solution is not a logarithm in 3D. Okay. So we started to produce some of these devices. This is an SEM image of one of these small bridges. This is an AFM image, and we started to play with AFM. We realized it's actually quite difficult to take AFM images of this 3-dimensional structure. So this image was actually produced by an AFM tip that had some carbon nanotubes decorating the end of it to actually go down deep into the trench. Okay. So with this in hand, we started to measure some DC characteristics, and I show the IV curves here. And in reality, the IC/RN product, the product of the current and the resistance, shown here was about 400 microvolts. Okay. And this agreed extremely well with this other cryptic result here that I write KO-1. So KO-1 is the Kulik-Omelianchuk-1 theory, right, which was, if I remember correctly, either in Uzbeki Fiziki Nauk or JETP letters, and I don't remember, from '79 or so. And this calculation, which is about 2 paragraphs, simply says we will solve the Usadel equations for fixed phase, and that's the best you could ever do for a weak link. So you can see in 3D we're getting pretty darn close to that structure, whereas in 2D we were far away from it. Right? In reality, your 2D junctions really are not very good Josephson junctions. They really look like wires. Okay. So this was again encouraging, and then we did John's favorite thing. We made squids out of this. And I think it was Fred this morning that said make many squids, so we made many, many, many squids like this, and started to measure the modulation depth of these squids. So it was Dale that pointed out this earlier in the morning that if you have terms that are not simply sine or cosine of phi, they don't necessarily cancel perfectly, right, in a sinusoidal pattern. Right? So a perfect tunnel junction squid will modulate to 0. Something with a different current phase relation will not modulate to 0. So in reality, this is the modulation depth of 3D structures and 2D structures. And indeed, you see we were getting very large modulations now in our 3D structures. So we saw this that was rather enhanced for 3D nanosquids. By the way, we made the 2D ones because they're really easy to make, and the 3D ones are real hard to make. So this was the easy way to compare these structures. So again, you can plot what modulation depth you would expect, right, as a function of length, and we were pretty close to this ideal model with 3D squids. So this was all DC transport. As many of you know, mostly we do microwave measurements. So the idea was once we actually have this element which we could understand and control, could we build amplifiers, could we build qubits, could we build all these other things with this building block? So the first thing was to do some calculations and figure out what the microwave response of such a device should look like. So this is the familiar RCSJ model, where I've replaced the current phase relation, which is normally a sine or a cosine, as you write it, with some f of delta, which is here. And we took our numerical current phase relations and started to calculate what would be the microwave response of such an oscillator. And that's what's shown here. So this is if you have a typical tunneling junction with a pure sinusoidal relation. What's plotted here is if I drive with microwaves as a function of drive frequency on the horizontal axis, drive current on the vertical axis, basically power, and the color telling me the phase of a reflected microwave tone. For low powers, I would see the linear resonance, the linear plasma resonance of this mode. And as I increase amplitude, I see the softening of the mode, the duffing part of the oscillator, and then I see some bifurcation up to here. If I did this now with this kind of almost sine-like current phase relation, it looks pretty darn close. Right? You should get something that looks pretty similar to it. For 2D, that's not at all what we would expect. In fact, you don't see and you don't expect this type of nice nonlinearity and bifurcation. So does it really happen? Well, it seems to happen quite nicely. So this is now a nanosquid with Q of 30, so it's a low Q device. And indeed, we are able to see a very nice softening of this mode and bistable region. And we were able to make parametric amplifiers out of these little wire devices. One thing I want to point out, and perhaps not dwell on here, is if you look at the tuning of this squid curve, there's something strange. It's actually hysteretic, even though it was not hysteretic in the DC IV characteristic. So the inductance properties of this device are actually quite interesting and very understandable if one spends a little bit of time on it. So we have now a device which tunes with flux. It's a squid, and we can measure small magnetic fields with it. We wanted to do something extra with this and say, could we amplify as well as simply measuring a flux? So we did the standard microwave trick here of driving the oscillator at some frequency omega d, right, as a pump tone, if you like, and then modulating the actual signal. This would be the magnetic signal you want to measure at omega s, right? So in reality, we would simply move the resonance curve back and forth at frequency omega s. And what that would look like in the frequency domain is a central carrier or your pump tone and two sidebands that are offset from this tone. So this is if we drive the circuit omega d in such a way that this is still linear. Right? The resonance looks like a linear curve. If I actually go ahead and drive it harder, I can actually get gain out of the system as well. So we can decompose this type of microwave squid into really a two-element device that has a transducer which takes now some voltage, some flux, and turns into an AC voltage. And this AC voltage can be amplified depending on how strongly you drive your squid. Okay. So if I only use this transduction effect, which is quite often the mode of operating a DC squid, right, in some kind of linearized regime, this would be the transduction. But in reality, I also have something that I call this paramp regime, where I can flux couple a signal, a real magnetic signal, and see how sensitive a measure I can make. So these were the results in a nutshell. If we were to operate these nanosquids in a paramp regime, we would measure 17 nanophi not per root hertz magnetic noise, which is quite a nice number in terms of magnetic sensitivity compared to squids. To show you, if we did not use this built-in amplification and kept the linear part of the squid, we'd measure something like 50 nanophi not per root hertz. If we used a 2D device, we'd have 360 nanophi not per root hertz. So the part here is where we're simply improving the transducer, going from 360 to 50, when we're making the actual squid itself more nonlinear, and then we gain this extra factor of a few with the built-in gain. We also demonstrated that even though it's aluminum, it seems to work just fine in 60 millitesla parallel field, which is reasonably practical for measuring some magnetic samples. Just to point out, by the way, this degradation beyond 60 millitesla was really the ground planes of our structure going bad, not actually the element. So there's significant improvements to be had in this device. Okay, so this was sort of the magnetometer amplifier aspect. Can we actually make qubits out of this structure? Right? Would they be perhaps better? How would one operate them? The qubit par excellence of that time was certainly the transmon. So the goal was, perhaps still certainly is the transmon. I'm looking at Robbins going back and forth. Was the transmon. But the transmon, of course, has a much smaller critical current than the things that I was showing you. So the goal, if one wanted to produce a transmon with this, would be to flux tune down to a much smaller critical current. So this seemed very reasonable for doing this. However, something very strange happened. And this is where the noise part comes in to the talk. This is now the flux, the microwave response at zero flux. You see a nice sharp resonance, which is there. If you now go ahead and flux tune it down, here's the normalized flux and flux quanta shown here, you develop a little shoulder, which is here. That's very strange. Absolutely deleterious to any qubit you try to make, because you just killed your line width by adding this flux. And this troubled us for at least a year. So what if you raise the temperature? So this is low temperature here. Focusing on this feature, which had a shoulder, if you raise the temperature, again, this feature seems to go away. So we started to think that perhaps quasi-particles are playing some sort of role here, and we consulted Leonid Glazman at this point. To summarize the final answer, in these weakling structures, as Christian was showing us this morning, the structure of the energy levels are Andreev bound states that are there. And these bound states have this particular energy level spacing, which depends on the transmission of your channel. If you have a tunneling junction, you have many channels that are very opaque. Okay? So this tau is very small, and your energy levels, in fact, are not modulated by the phase difference across your Andreev structure. What Christian was showing this morning was something that had near unity transmission, 99.6% or something like this. So if you start looking at this for very high transmission near unity, in fact, you have this as your level structure. So what happens, in fact, is you have a very nice trap for quasi-particles if you flux bias your structure at finite flux bias, which is here. So the idea was perhaps we're trapping quasi-particles, and if that's the case, can we untrap them by simply microwave exciting at this level frequency, which is here? Okay. That came second. The first question was, well, how many quasi-particles are really needed, in fact, to reproduce this effect? This is the theory that Leonid and his group produced. Assuming that you had zero flux and no trapped quasi-particles, you could fit the line shape. The little shoulder on your line shape was fit with an n bar of 0.49. So this is an n bar, or average occupancy of quasi-particles, not of photons, in this particular cavity. It corresponds, if you put it in volume fraction numbers, to about 1 part per million or so, which is the usual number we talk about for quasi-particles in superconducting structures. So that seemed to indicate that this is a decent mechanism. Can we really get rid of this quasi-particle to verify this being the case? Can we do this particular effect? It seemed to work extremely well. Right. We'd find the frequency in microwaves, and you see the same curve that I showed you with those shoulders, they all go away. And in particular, you can do the usual thing that we do as microwave people. You can do spectroscopy. You can figure out where that level is and track it, and so on and so forth. So this seemed to be a very bona fide explanation, if you like, of the quasi-particles. However, this was basically our last work on this subject. There are several things that still remain open questions here. Part of the reason of us not pursuing this for qubits is that at some point along the way we realized that tunnel junctions are really good, right? And in fact, not limiting our coherence effect. So a little bit of that motivation went away. However, we have not done the experiment of sensing individual magnetic elements, right? The goal that we really wanted to do in this work was to come up with the dual of the SET, if you like, a detector that would measure single Bohr magnetons. The sensitivity number that I quoted you, the 17 nanophi per root hertz, if you translate that into a spin sensitivity, one should be able to calculate 0.3 Bohr magneton in 1 second of integration, even if you're 100 nanometers away from the weak link. right? So that's about 1 Bohr magneton within 100 nanometers in a second. So that's a reasonable number to try to obtain. But as you can imagine, that's a hard experiment to do. If we tried to measure a spin a half, as Gert told us this morning, there's lots of spin a half, and Robert told us all around, right, the structure. So you have to measure something perhaps with zero field splitting like diamond or silicon, so on and so forth. So all of these things are rather challenging to do. So that's a set of experiments we did not do on the sensing side, but even the statistics of these numbers are very interesting. In this plot, you may ask, the average is 0.49, but really, what are the statistics of the trapping, right? And it turns out the distribution that's going into this doesn't seem to be Poissonian, right? It seems to be heated like many things in our qubits and cavities. It doesn't seem to obey a very simple thermal distribution, right? So herein may lie some interesting physics about how quasi-particles are being trapped and untrapped. And in reality, with the paramps and traveling wave amplifiers today, we could probably very rapidly figure out the individual events as they go in and out. That's an experiment that we have not done, but maybe a useful thing to do when studying quasi-particles. So in summary, what we observed were multiple resonance peaks in a very simple circuit, just a flux-biased squid oscillator, but made with a nanosquid. This seemed to be rather consistent with the structure acting as a quasi-particle trap under flux bias or phase bias, simply because of the Andreev level structure, which we verified in spectroscopy, right? And roughly around the same time, the Saclay folks put out their beautiful experiments that Christian also talked about in the morning. Okay. Like I said, the quasi-particle distribution, shoved under the rug a little bit in this talk, is thermal only at high temperatures. Right? At low temperatures, it's still a bit of a mystery as to why we have this. They are certainly non-equilibrium. What is the source? What do they depend on? This is an open question. So it would be perhaps a very nice thing to look at the full frequency spectrum of noise in such structures to probe how long the relaxation takes, how long does it take to trap a quasi-particle, untrap it, so on and so forth. And in principle, with the tools that we have today as a community, we could look at single-shot detection of these quasi-particles. So I want to stop here and thank you for your attention, and of course, congratulate you, John, once more.
All right, questions for Irfan?
I feel like going back long in the past, because in the 70s, we made microbridges, day-in bridges, and we found that 2D systems didn't work. There was heating, which you call non-stochastic quasi-particle occupation or something, but heating was around the corner. The coherence length, these experiments were done close to TC, so coherence length was long. That was not the issue. But indeed, in 2D, it doesn't converge. You don't have the right boundary conditions. And we did calculations in Ginsburg-Landau, actually on an analog computer, around 75 or something. And then we showed that 2D didn't work in Ginsburg-Landau and 3D did. But also in experiment, we made bridges, variable thickness bridges, by scratching. And the 3D ones, the variable thickness bridges, I think we used that for the first time. They worked. I mean, they had nice Shapiro steps and all that.
Indeed.
There was a huge difference.
Oh yeah, there's a lot of beautiful work by Octavio, for example, and others for these VTBs, as they were called in those days. So you're absolutely right. What was interesting to us is we were working at low temperatures, where Ginsburg-Landau, of course, the mean field approach does not give insight in terms of the transport. And in reality, if you heat up a bridge close to TC, they all look very good. And that's sort of the advantage. The trick for us, for magnetometry, we can get away with that, because we just want to use it perhaps as a squid. For qubits, we would obviously have a problem because of the quasi-particles. So the AC properties, it turns out to be different than the DC ones. And that was a bit shocking to us. But you're right, there was a very long history of bridges and nanosquids, and we wanted to see, in fact, how that would translate into the microwave.
Other questions?
Yeah, I wonder what is the meaning of this average number of quasi-particles that you mentioned, because this is a diffusive system with very many channels. And there are many, many possible traps in some sense. So this is a global average number?
This is an average, and it's to be realized for that particular experiment, it's a resonator, right? So it's not simply a DC junction, in which case it would not make sense to talk about an occupancy. So we're talking about a resonator, and in this resonator, on average, how many quasi-particles are there, given the Q of the kappa of the resonator. In the same way that you can talk about the number of photons in a resonator.
Other questions? Is there one back there? I couldn't tell. No? Okay, maybe let me end on a particularly tough question then.
Okay, very good.
That must be appropriate for Irfan. So I guess in the sort of spirit of quantum coherent science, maybe two related or interrelated questions. What do you think is maybe one particularly intriguing direction in your perspective, and also one particularly important challenge facing sort of quantum coherent science moving forward?
Relative to this talk or in general?
Relative to whatever you like.
Well, I will do the usual thing, which is to answer some question which kind of sounds like yours, but is not that one. That one's too hard. I think this is the question I asked Michel in his talk, and we're going back and forth. As a physicist, what I find very interesting is to look at, is it time to reinvent quantum mechanics? Every 100 years, we reinvent our theory of physics. So in fact, what if any boundaries are there in this theory? What if any size constraints that are there? And this I find is a very interesting question that we look at in this qubit science, if you like. What happens as you increase the complexity of your system? What happens to coherence? Where does it flow? Where does it get distributed? What happens to your cats as they evolve from embryonic to kittens to large, lazy animals, as they get larger? So this, I think, is for me sort of the interesting question. And the challenge will be, even following Gervin's law, how to maintain coherence, but not simply in the static state, but in the active state as well. Right? How do we actually keep coherence alive by active manipulative methods and feedback methods? So for me, I think these are sort of the challenges. How do we sort of push beyond a certain threshold where even though we have Gervin's law of requiring better coherence, but maybe we can achieve that by active methods, and then really tackle this question of what are the fundamental, perhaps, limits or boundaries of quantum effects. So I'm sure that did not answer your question, but that's the best I can do later in the day.
Let's thank Irfan again for an exciting talk.